So we have 142 of Leetcode, linked list cycle 2. And before solving this question, let's look at the time constraints that we have. The number of node can be from the range of 0 to 10 raised to the power 4. So the maximum number of nodes that we can be given is 10 raised to the power 4. Now let's find out the maximum time complexity that our code can have. We have a time complexity of O n square. This will get us 10 raised to the power 8, which is going to be above 10 raised to the power 6 operations. In Leetcode C++, we know that we can perform around 10 raised to the power 6 operation under a second, right? Now, what if for the n log n case? Now, n is 10 raised to the power 4. 4 times 10 raised to the power 4 will actually walk under the time complexity. So, our code, our maximum time complexity can be n log n, right? So, n log n. Now, these are the values that we are given. The node value can be from minus 10 raised to the power 5 to 10 raised to the power 5. So we can simply use int if we have to work with the values. And the position is -1 or a valid index in the linked list. We'll see in the question. Now, our question simply states that you are given the head of the linked list, return the node where the cycle begins, right? So if there is a circular linked list, we have to find out the starting node of the circular linked list from the head, right? Starting from the head. Now, this question is an extension from the question 141 of Leetcode, linked list cycle. This is an easier version of the problem. You first need to check this question out, then come to this question. The first step is, the detection of a loop. Detection of loop. And the second step will be finding the starting node in circular linked list. Now, specifically, the step number 1 is covered in this question, in this easier version of 141 of Leetcode. We will discuss two methods to solve this question. The first will be the brute force way. We'll use a map or a set. And second, we'll use an optimal way using the Floyd's cycle detection algorithm. Now, let's say this is the head of the linked list that we are given. Now, the brute force way of solving this problem would be, we could take any unordered map or a set or an unordered set. Let's go with an unordered map. Let's say we have an unordered map. Now, what we will do is we'll iterate from the head. Let's say fix a pointer mover starting from the head, and we'll move till we reach a null, right? We'll move till we reach a null, and every single time we move our mover pointer, we will check if the node address is present in the unordered map or not. Now, node value can be repeated. I can have two ones, but node address cannot be repeated. If it is repeated, then we will be able to find the starting node. Now, what we will do is, let's say we are at the first node, so we'll check if this one is present in the unordered map or not. If it is not, then we'll simply push it. So we have one. Now then, and we will take any integer value, let's say, for example, we'll push 1 into it. Then we'll go to 2. Now 2 is not present in the map, so we'll push 2, right? Similarly, we push 3. And similarly, we will keep pushing 4, 5, 6, right? 4, 5, 6, 7, 8, 9, 10. And when we will come back here, again 3, we'll check if 3 is present or not the value. Again, I'm saying we have to check the address. So unordered map, the type of the unordered map would be the node star, right? Let's say UMP, the name of the map. The basic idea is that we'll start from the head and we'll keep on iterating until we find null, and we'll again come back here and we found out that 3 is already present in the map. So we'll simply return 3 as our starting node, right? So 3 is already present, we found out. So we'll return 3 as a starting node. What if we have a linear linked list? So we have something like this. So we'll reach a null. Once you find a null, you can simply return that there are no starting nodes. We can simply return null, right? So the code would be really simple. Now, talking about the unordered and unordered map and only map. First, what we can do is we simply implement unordered map, and if we get a TLE, we can shift back to a map, because for unordered map, the time complexity for insertion, deletion, and searching is around O1, and for the hash collision, it can go up to ON. But for map, the time complexity of insertion, deletion, and searching is O log n. So implement unordered map, and if you get a TLE, come back to map. Now the code is very simple. First you define the unordered map, and then you start from set the mover in the head, start iterating, and once you find the node, repeat it twice, you simply return that node, otherwise return null. So we'll simply have done the same thing. We defined an unordered map. This is our unordered map we defined. Then we set a mover to the head. Then we ran a loop while mover is not equal to null. If mover is equal to null, then we know if it is simply a linear linked list. So we'll simply return null. Before pushing into the map, we have checked if it is not, if it is present in the map or not, then we'll simply return the mover. And if it is not, then we have stored it into the map mpp.mover equals to 1, and it could be any value. We could have set 5 into it, right? It could be any integer value. And then we have moved the mover one step forward. So mover is equals to mover.next. Now talking about the time complexity, let's say for any linear linked list or a circular linked list, we have to visit all of these nodes at least once. So the time complexity will be on. And for the space complexity, we are using an unordered and extra space. So it will be also of the order on. So now we will see the optimal way of solving this problem using Floyd detection algorithm, or also known as fast and slow pointer. What we will do is simply we'll assign a fast pointer and a slow pointer at the head, and we'll keep moving the fast and the slow pointer. Slow pointer moves by one step and fast pointer moves by two steps, and you keep moving them until they meet at one node, right? So you move slow by one and fast by two, again move slow by one and fast by two, move slow by one and fast by two. So we found a node where slow and the fast pointer meet. Now what you do is you take any of this pointer and set it to head. Let's say we set the slow pointer to the head, and you keep moving them one step forward. You move the slow pointer one step forward and simultaneously move the fast pointer one step forward till they meet again. So you move the slow by one and fast by one, move the slow by one and fast by one. Now you see that they meet at one node again for the second time, and this will be your starting node. This will be your starting node, and you have to return this node. Now first I will discuss the code, and then I will get to the logic part of why this method works. Now what we actually do is first we set this fast and the slow pointer to the head. So we'll do the same thing. Fast pointer, we assign it to the head, and the slow pointer is assigned to the head. Now for the previous 141 of Leetcode, the easier version of the problem, we saw the while loop must be if fast pointer is not equal to null and fast next pointer is not equals to null. This will be again the same condition that we will use, and if you have any doubt, go and visit that problem. So we'll write the same condition here. So while fast pointer is not equals to null and fast next pointer is not equals to null, we'll simply run a loop. Now inside the loop, what we will do is we will move the fast pointer by two steps forward and the slow by one. So move the fast by fast next moving it by two steps forward, and for the slow we move it by one step forward. So slow next one step, and then we will check key for the first time when the fast and slow pointer are meeting. So this will be the first time. So we'll run a if condition key if fast equals to slow. If we have fast equals to slow, what we did was we took any of these pointer, either the first or the slow, and set it to the head. So we'll simply set this to the head. Let's say we set the slow pointer to the head. Then we ran a while loop. And move the slow pointer by one step and the fast pointer by one step, and keep moving until we find a node where slow and fast meet. So we'll simply again run a while loop. While slow not equal to fast, move the slow by 1 and fast by 1. This is what we have done, fast by 1 node. And then at the end of it, we'll actually have the starting of the linked list. So we'll return either the fast or the slow, because they're both pointing at the same node. Return fast, let's say. And this will be our end of the code. So this is inside the if statement, and this if statement is inside this while statement. So if this is not circular, outside this while loop will simply return null, because we don't have a node of a circular linked list. Let's talk about the time complexity that we have. Now this code, in this code, we have to at least visit every single node once. So the time complexity will be O of n. And for the space complexity, our code will be O of 1, because we are not using any extra space. Now we'll look at the logic part of why this problem works. Now tell me, when the slow pointer will be at a node 3, let's say, let's take for example, well, where would the fast pointer be? Will be at the node 6, right? So if slow moves by distance, let's say a, the fast has to move by distance from the head to a. So this distance will also be a, right? From the head we are talking, fast pointer moves by 2a, and the slow pointer moves by a, because fast is moving twice as fast as slow. So let's call the remaining distance from the 6 all the way up to node 3 as b, right? Now tell me the distance from the fast to the slow. So if you count the node from the fast to the slow, we have a distance b, right? We have a distance b. Now when fast is moving 2 units towards slow, right? Fast is moving 2 units towards slow, and slow is moving away by 1 unit from the fast. So the net distance, the relative distance between them, is decreasing by 1. So eventually we know that b is going to be from b minus 1 to b minus 2, and eventually it is going to go to 0. And we also saw that they are colliding at node 12. So fast and slow pointer were meant to collide at any of the node, right? Now tell me, how much distance did the slow pointer and the fast pointer move? We had b steps performed to get to 0. So our slow pointer was at node 3 initially, and the fast pointer was at 6. Now after b number of steps, slow pointer and the fast pointer met at 12. So slow pointer had incremented every single time, it incremented by 1. So slow pointer had to move b distance, right? We can say from the 3 to get to 12, slow pointer had to move b distance. And how much did the fast pointer had to move? 2b distance. Now we clearly saw that slow had to move from 3 all the way up to 12 and perform b distance. So how much distance is left? From 3 to 12 is a, right? The distance from node 1 to 3 and the distance from node 12 to 3 is same. So this is why we set one pointer at the merging point, any of the fast or slow pointer, and one pointer at the head, so let's say slow pointer, and we move them one step forward until they meet at the starting node. So this is the logic part of the problem.